All right, we need to review the values of the constant a that makes this function continuous. So for the first part, we do need to check to see if our function, let's say for part A, is f at 1 defined, and that's always going to be our first step. And notice it is defined right here. So we'll come back and find that actual value if we need it. Most of the time when we look at our limit values, that's going to give us enough to be able to solve for our variables. So we're going to look at the limit as x approaches 1 from the left of our function and see if that's equal to the limit as x approaches 1 from the right of our function. So here from the left, that's all the values that are less than 1. And I'm going to substitute a 1 in for x. So I have 0.3 plus a. And then on the other side, the limit as x approaches 1 from the right, I'm going to substitute in, and I have 0.4 plus 2. So that looks like we have 0.3 plus a equals 2.4. And so solving this for a, it looks like the value needs to be 2.1. Okay, moving on to the next. Again, same scenario here, and we do see that f at 2 is going to be defined. So let's go ahead and address the limit from the left. So the limit as x approaches 2 from the left of our function, and that's got to be equal to the limit as x approaches 2 from the right of our function. And the limit from the left, all these values that are less than 2. So that means I'm going to have a minus 2 equals, and then on the other side, if I sub in a 2, I'm going to have 4. So notice that our a value's got to be 6. And again, continuing the same pattern, again, we're looking at our limit value from the left and our limit value from the right. So here we have the limit as x approaches 2 from the left of our function, and we need to know is that equal to the limit as x approaches 2 from the right of our function. So the limit from the left, we're going to sub in a 2, so I have 2a equals, and so from the right side, again subbing in, that's going to be 9 minus 4. So here I have 2a is 5, so a must be 5 over 2. Okay, for our next problem, we're going to continue the same patterns. And so my limit as x approaches 1 from the left of our function, again, needs to be equal to the limit as x approaches -1. I forgot my negative there. From the right. And again, it's just a matter of subbing in and setting stuff equal. So if I sub in -1 for x, that means I have a negative a plus 5. That needs to be equal to, well, -1 squared is just 1, so I'm going to get an a. So notice 5 equals 2a, and so 5 halves is going to be a. All right, and let's see, over on the other side, again, continuing on the same pattern. And so now we see that the pattern is subbing in. So that's going to give me negative 0.4 plus a squared has to be equal to, and again, subbing in. So I have negative a minus 1, or no, plus 1.6. Okay, so getting everything together, I'm going to add our a's over, because it looks like we're going to have to set up a factoring situation. If I subtract 1.6 over, I'm going to get 2. And so we're going to factor this, and we're going to get a plus 2 times a minus 2. Oh, no, a minus 1, sorry. It's late. I'm tired. And so we set each part equal to 0, so a is -2 or a is 1. And so we see that we have two different values of a that is going to make this particular function continuous. Okay, again, on the same idea here, we are subbing in and setting equal. So sub in here, I'm going to have a squared minus 4 has to be equal to 2 times 1.5 times a. And again, this is setting up a factoring situation. And it looks like our factors are going to be a minus 4 times a plus 1. And setting each part equal to 0, notice we get negative 1 and 4. Okay, so starting off with our function, notice that this can be reduced. So let's go ahead and factor this. We're going to have x squared, or well, x minus 3 times x plus 3. And that's all over x plus 3. And notice those will cancel each other out, so I'm left with x minus 3. However, we need to take note, though, that here at x plus 3, we had a removable discontinuity. And so to find out where it was, let's go back and plug in. And so I have negative 3 minus 3, so I have negative 6 is where my hole in the graph is. So here, let's go ahead and graph this just to make sure we see what's going on. You don't necessarily have to, but it's always a good idea if you can. So right here's the hole in the graph. That is our removable discontinuity. So somewhere over in here is our hole in the graph. So we have this open circle, and we also know that we cross, this is just the equation of a line, and so our y-intercept is here at negative 3. So we have something like this going on. And that makes that a little bit easier to talk about your limit from the left and right. Again, keep in mind this ordered pair here is negative 3, negative 6, right? So again, when we're talking about the limit, we're really talking about this line that has a hole in it. So if we talk about our limit as x approaches negative 3 from the left, that is going to be negative 6. And from the right, it's also negative 6. And again, we can sub in that negative 3 and get negative 3 minus 3. And then our limit as x approaches 3 is negative 6. However, f at negative 3 does not exist. There is no value there for it. All right, so part E is continuous at, so it's asking, is the function f of x continuous at negative 3? So here, this is not continuous, so not continuous because, and so we make sure we answer the why or why not. And that's because f at negative 3 does not exist. And this was a removable discontinuity because we have a hole in the graph. All right, moving on to the next. Okay, so this one we have a piecewise function. And we need to look at and see, well, what is going to be our limit as x approaches negative 2 from the left? So negative 2 from the left, that's all the values that are less than negative 2. So we would sub in here, and we have negative 6 plus 4, so we're going to have negative 2. And now let's approach from the right side, that's all the values greater. And so that looks like that's going to give me 5. And so the limit as x approaches 2, unfortunately, is not going to exist because the limit from the left does not equal the limit from the right. But now we do have a for sure value for f at negative 2. That's going to be the or equal to situation. And if I sub in negative 2, I get negative 6 plus 4, so I have negative 2. All right, so here we need to talk about what kind of discontinuity. Well, I guess we need to answer we are not continuous. And we're not continuous at x equals negative 2 because our limit doesn't exist. Because the limit as x approaches negative 2 of the function does not exist. Now, what kind of discontinuity this is? Well, these two limits being so different, that means as we're coming in for negative 2 from the right side, So from the right side, negative 2 from the right side, we're up here at 5. And then if we're coming in from the left side, we're down here at negative 2. And I guess that one needs to be open. This one needs to be closed. So notice that we've got a line here and we've got a parabola here. This is a jump from here to here. That's going to be a jump discontinuity. And you know that because your left-hand limit and your right-hand limit are not equal to each other. So here, this type of discontinuity, f of x has a jump discontinuity at x equals negative 2. All right, moving on. Okay, now again we're trying to find the value of k so that the limit as x approaches 4 of the function exists, and this is just like earlier. You're going to plug in 4 to the top and bottom and set them equal to each other. So here we're going to get 12 plus 2, so I have 14 equals, and again here I'm going to plug in, so that's going to give me 20 plus k. So notice that k must be negative 6 for us to have that limit to exist. All right, so now this one wants both sides to exist, and this is a great example where you might have to do a system of equations. So again, the plugging in and setting equal is still going to be the same thing. So I'm going to plug in negative 3 for x here, and so I have negative 6 minus a has to be equal to, and if I plug in negative 3 down here, I'm going to have negative 3a plus 2b. And I would try to get my variables together. So I have negative 6 equals negative 2a plus 2b. And you can reduce all that down by a 2, so I suggest you do so. So that's going to be our first set of equations. Now we're going to repeat this process. However, we are going to do that with positive 3. So with positive 3, notice that's going to be working right here. So I'm going to sub in positive 3. So I'm going to have 3a plus 2b. And then on the other side, that's going to be equal to b minus 3 times 5, 15. And of course, I'm going to move that b value over. So I have 3a plus b equals negative 15. And so notice that with these two equations, to get a variable to cancel, I probably need to multiply. I would just multiply by a negative 1. And that should cause those b's to cancel. So that's going to give me a positive a negative b equals a positive 3. And so I'm going to have 4a equals negative 12. So a's got to be negative 3. So now I have a. So backtrack to one of your two originals and sub in to find b. And this one looks pretty easy, so I'm going to use it. So I'm going to have negative 3 equals the negative of negative 3 plus b. Negative 3 equals 3 plus b. And so b is going to be negative 6. So notice we have negative 3 and negative 6 for our a and b values.